Oh, right. Mouse.
But you can just press return.
Okay.
No?
Yeah.
Click C, the mouse will shut.
See.
And then if you forget this, there we go. If you forget that, we luckily have it recorded.
So I can go back and be like, how did I do that?
Yeah, and you don't have to speak in here. We have mics all over the room.
Okay.
Today we're very happy to have Alyson Brooks, who's at Rutgers. She was a graduate student at University of Washington, and then she was a Granger Fellow.
Okay. No, that was at Caltech, actually. So
Okay,
I forgot about the Caltech part.
Oh, yeah, at Caltech
Yeah.
and Wisconsin, and then
then
has been in Rutgers for about 10 years. And she's going to talk about simulations of low luminosity galaxies, which is actually, when I first met you, the talk I gave at the University of Washington was about the importance of studying isolated low luminosity galaxies, which I didn't work on after that, but so I'm very excited
and I
to
didn't
hear.
work on at the time.
Yeah, so I'm very excited to hear this.
All right.
Thanks.
Yeah, and maybe I should just, apologize in advance to the dark matter people in the room, because I'm not, my other hat, right, is to work on dark matter in these simulations, and I'm not showing any results from that work today. So I'm focusing on dwarf galaxy evolution today. So here's an example, right? So this is taken from a Milky Way mass galaxy simulation. This is just a dark matter map, and here we've highlighted some of the sub-halos, satellites of this Milky Way. In fact, there is actually, I don't know if you can see it, there are stars in this box, right? So this is the highest resolution ever published Milky Way, and so the whole point being that we're starting to probe down into the range of the ultrafaints, and so that's what's in that box. Is there's actually a few stars in there, right?
Yeah, I think it's our projector. I think our projector.
No, it shows up really well on the screen. So,
Yeah.
And I am rerunning many of these simulations in self-interacting dark matter as well, but those are still running, and so I don't have the results to show you today. So I'm going to focus instead on some of the results from the CDM version. So, but happy to have long discussions about SIDM after this. All right. So I guess I'd like to, especially for the new people in the room, remind people that it's just been over a decade that we've actually made realistic dwarf galaxies in simulations. And what I mean by realistic is bulgeless. Okay, when I first got into the game, everybody was talking about the fact that you couldn't make bulgeless dwarf galaxies. And by bulge, I mean a stellar bulge sitting at the center. So this is not a simulation, right? This is a real galaxy. But it can be described by an exponential disk all the way down to the center. There's no stellar bulge sitting at the center. And like I said, when I first got into this in grad school, everybody was saying you can't make realistic dwarf galaxies because they always ended up having a big stellar bulge sitting at the center. Okay, well,
is this like 10 to the 9 stellar mass, or?
10 to the 8, 10 to the 9, yeah, either one. Most galaxies down in that mass range, right, are bulgeless. And so I'd like to say that there was like some magic that we came up with that fixed everything. Maybe I should be really glad there's not some magic we came up with. It was resolution. Right? When we went to higher resolution and started to be able to resolve the high density regions that look like giant molecular clouds, that changed how feedback was interacting with the gas in the galaxy. And then it started driving galactic winds for the first time, and it blew out all the low momentum material that would otherwise go on and form a stellar bulge. Okay. So then I think you can ask, in that time, how much progress have we made? I don't know. Right? Well, we'll talk a little bit about that today. But we're about to be confronted with a huge amount of dwarf galaxy data over the next few years. So I've highlighted some of the upcoming, observational results from LSST, right, the Legacy Survey of Space and Time at the Vera Rubin Observatory, the Marian Survey, which you may not have heard of, but I'll mention, and Wallaby, which is an SKA Pathfinder and is already taking pre-survey data. So let me go through each one of these and tell you about some of the dwarfs that they're going to find. I still love coming back to this plot that Eric Tolliver made, over 15 years ago now, that shows the known satellites of the Milky Way at the time. And so what you're seeing here is the radius to which we are complete for a given magnitude, right? And so down here in the ultra-faint range, we're not even complete up to the Milky Way's virial radius. These things are so faint that they very quickly fall out of the completeness of the survey. And then as you go to brighter things, you can see them farther away. Right? So there have since been, new ultrafaints. We could add a couple dozen more down in here found by DES since the time this plot was made. But the main takeaway for you today is to look at the co-added LSST results, right? So we are basically going to find out to about a megaparsec all of these faint things, right? And this plot is here to remind you that it's not just because they're faint that we haven't found them, right? It's because we haven't looked at the whole sky yet. That's the Sloan footprint up there.
I was just.
Yeah. Is this it?
So that will work, yes.
Yeah,
You need a
I'll do
laser
this.
pointer. The physical pointer I just had, but I don't know where.
Okay, this will work. Right, so here is, most of SDSS pointing out of the galactic disk towards the North Galactic Cap. And then there's also these tails down here towards the Magellanic Clouds. And DES was also focused down here, right? So there are just whole regions of the sky that we haven't explored yet that LSST will. And so these plots together better quantify it. Here's a nice, from Josh Simon's review on dwarf galaxies. If you say look at magnitudes down to -4, LSS, that will be complete out to a megaparsec for LSST. And then if you come back over here to this plot from Polarid, that basically gives you hundreds of ultra-faint dwarf galaxies within a megaparsec that we're going to find, right? That we expect to find. And that all assumes that CDM is correct. But I think at this point, we don't have any reason to think it will not be. And so hundreds of ultra-faint dwarf galaxies. That is, of course, searching for things through stars. There's another way that Wallaby is going to open up, which is to actually find dwarf galaxies through their gas. And this has been done before. I don't know how many people have heard of SHIELD, the survey of H1 and extremely low mass dwarf galaxies. But the initial SHIELD sample was all found in alfalfa, right? So they identified these gas clouds, these H1 clouds in alfalfa, and then they went back to SDSS and they found, hey, there are stars there, but they were so faint or low surface brightness that they hadn't been identified in the SDSS catalog. And so Wallaby, this is the completeness limit here for Wallaby, or the detection limit, I should say. And so it opens up the possibility of finding all of these low mass dwarf galaxies within a few megaparsec, actually, in gas, not just in stars. And so I think actually, some people, it occurs to me now, there's probably some people in the room who are thinking, yes, but they're dwarf galaxies, they don't have gas. And I think actually we're going to find that we're wrong on that. And I'll come back to that.
They definitely have gas.
They
All the
definitely
dwarf
have
galaxies
gas.
have gas.
That's my thought. All right. And then the other survey I mentioned is Marian. All right, so Marian is a ground-based survey that's happening right now. It actually should be finishing up this semester. It's led by Alexei Leotoud at Santa Cruz and Jenny Green at Princeton. And they have specially designed filters that are essentially targeting the star formation emission lines in dwarf galaxies in this redshift range, so 0.06 to 0.1. And in other words, they're going to end up finding about 100,000 star-forming dwarf galaxies between 10 to the 8 and 10 to the 9 stellar mass. Okay. Now, the fun part of this is that, with Alexei as the lead, what she wants to do is to stack these and actually do weak lensing on these dwarf galaxies. And so we're actually going to get a direct measurement of the halos in these low mass things for the first time as well. And we'll be able to do abundance matching and galaxy halo connection and work down into a lower mass range than we've ever gone before. Okay, so hopefully I've convinced you. We've got a lot of data coming in. I don't think theoretically we're prepared for it, right? So my collaborators and I have been preparing for it. by running a whole suite of dwarf galaxy simulations to try to make some predictions for these upcoming observations. Okay, so what you're seeing here, our approach is actually, there are two ways you can run a simulation, right? You can run a whole box, all at the same resolution, or you can put all of your resolution on a high resolution region that gives you, one galaxy usually, a Milky Way or some dwarfs. And what we've done actually is run a zoom region like that, but we've put it on dozens of dwarf galaxies. We've put all the high resolution on a cosmic sheet. And by doing that, we actually get out dozens of dwarf galaxies at a time. And we've done this multiple times in order to develop the statistics. This is my code, Changa, right? So the reason I like to leave this here is that we tried this when we used to use gasoline, and the thing like ground to a halt immediately. But with Changa, it just, no problem. I can run these volumes very easily. So Changa scales very well.
Sorry, the choice, you sort of by fiat just said there's a particular wall we're interested in, and we want to resolve all the galaxies in this wall.
Yeah.
And instead of picking out an individual galaxy.
Right. Yeah. I mean, the whole, like I said, it's a zoom region, right? So it's actually a 25 megaparsec on a side box.
Right.
And then somewhere in there, we put all our high resolution on a sheet that gives us dozens of dwarf galaxies.
Well, how many luminous? I guess. Okay. All right. So it's a handful of luminous galaxies in that box.
Yeah. Somewhere from a couple dozen to about 3 dozen usually.
Yeah.
And I should say, I mean, like I said, it's still the full box, right? 25 megaparsecs on the side. So there are massive galaxies in there. And so in the end, right, I say this is comparable to the local volume.
Your legends are invisible to me. Is
Yeah.
this the whole box or just the zoom?
This is the zoom
Is
region.
the zoom in part?
Yeah, so this
And
is
so what
gas.
are the masses?
Yeah, you're
What
right.
is the gas density?
Gas surface density, here's 10 to the 3, here's 10 to the 7. And then, of course, this is dark matter density, here's 10 to the 4, here's 10 to the... What is that, 2?
I guess.
I think it's 2, actually.
No, oh yeah, you're right.
Yeah. So this blob of dwarf galaxies ends up being about 3 to 10 megaparsecs away from something like the Milky Way, right? The Milky Way is still in the box, but it's out in the low resolution region without any hydrodynamics. And so that's why I think of these as comparable to local volume, right? The local volume is about a megaparsec out to about 11 megaparsecs from the Milky Way. So here they are, right? We're calling these either the Marvel dwarf volumes or the Marvelous dwarf volumes. You were just looking at Captain Marvel, but we have, Electra, Rogue, and Storm as well. And so these are incredibly high resolution. You can see the stellar mass. The star particles are born with 400 solar masses of stars in them. They're a population with about 400 solar masses of stars. That means that's what allows us to actually get down into the ultrafaint range, right? So we can resolve the ultrafaints either in the field in these volumes or ultrafaints as satellites of other dwarf galaxies. And so as I said here too, we're running them in different ways, including with SIDM, but I'm not going to be talking about most of that today. Okay, so these are the local volume. Okay, LSST of course is going to find stuff I mentioned, within about a megaparsec of the Milky Way. So to complement these, we also ran the Justice League suite of simulations, right? Yeah. So you can see we sort of stuck with the comic book theme by going with the Justice League, DC Justice League, Marvel, DC. Except we liked being able to name our simulations after women, and the Justice League actually doesn't have that many women in it, right? So our Justice League is the first 4 women who have served on the Supreme Courts in Washington, D.C. So there you go. And again, so these are complementary to the Marvel runs with stellar masses. Actually, so 2 of these, Sandra and Elena, have been run with the highest resolution yet published. That's what I was showing on the first slide with Sandra. With 1,000 solar masses in a star particle. So again, we're actually being able to get down into the ultrafaint range around a Milky Way mass galaxy for the first time.
SPH resolution is like the gas particle smoothing one? or
It's the
something?
smoothing, yep, yep, exactly. And that's about the limit of what I intended to talk about with the simulation, so if you have other questions, feel free to jump in. Wanted to actually get to the results. All right, yeah, so these are the two with the high resolutions. All right, and then added to that, right, so in order to do theory for the Marian survey, those are mostly, like I said, 10 to the 8 to 10 to the 9 stellar mass. It's Magellanic mass dwarf galaxies. So we're also running a whole bunch of new Magellanic mass dwarfs, about 20 of them. I'd say we're about halfway done with the CDM versions, and some of the SIDM runs, like 1 or 2 of the SIDM runs, I think, is finished. These are 2 different galaxies, and I just wanted to show pretty movies because that's what we do. This one here is a map of the stars. That's the purplish pink stuff that you'll see at the center here, plus a gas temperature map. So mostly you see blue, that's cold gas, but maybe you see that when there's some feedback going off, you'll start to see some green and red as the gas gets heated up by the feedback. And this one over here, like I said, is a different galaxy. And now we're just looking at the gas in this galaxy, not the stars, no dark matter. And it's color coded based on its metallicity. And I just thought, I think maybe this projector is not most colorful, but yeah, I just thought, you know, the mix of colors in this movie was particularly great.
What would happen if you rotated that screen? Do you think that would work, Mike? And
You want to see it?
I just wondered. If you
Oh, yeah, well,
looks
yeah,
great
you
up
can,
here,
you
yeah.
can rotate that and
we can
you'll,
just get an idea of.
yeah.
Nice.
Yeah, assuming you can see it. So.
You definitely need a new projector.
Yeah, we were the same way at Rutgers. So. All right, these went on for several minutes, so I was probably going to move on. Maybe one thing I'll point out, because I will come back to this, is that you'll notice these Magellanic mass galaxies are kind of disky looking, and that's a feature. So here they all are combined, except for the Magellanic mass galaxies that I just showed you. So the Marvel and Justice League dwarfs together yield over 200 dwarf galaxies. This is their stellar mass average of 0 as a function of their peak halo mass, right? So many of these, the ones that are stars, are satellites of other galaxies. And so we take their halo mass before they fall into a larger halo and start getting tidally stripped. Right, and so that gives you the stellar mass to halo mass relationship. The colors here are different abundance matching estimates from other groups. And so you can see how we all compare. We're all in roughly good agreement, actually, I'd say.
I mean, in an observational plot, this would be the lower end of the Tully-Fisher,
Oh, yeah.
and so.
I mean, we're down, right, so here we are, we're going
Yeah.
down into the ultra-faint dwarf range. Here's the
Yeah.
LMC-mass galaxies
Yeah,
here.
so up there, is there less scatter here than you would
Yeah,
expect? Okay.
Yeah, there, no, not that we would expect. It is pretty well
Well-
known that around Milky Way masses, right, the scatter is actually small. It's like
Yeah.
0.2 to 0.3 DAC.
But this is well below the Milky Way mass, right? I mean,
Yeah.
between
Yeah.
10 to the 7, 10 to the 8,
So-
I would have expected more scatter in this y-axis.
Or scatter. Okay.
Expected because?
Sorry, not maybe expected, but observationally, that isn't that the regime where
It
the
usually
Tully-Fisher relation becomes steeper and broader,
Oh,
whereas
okay.
the baryonic Tully-Fisher
We'll
relation.
we'll
Okay.
kind of come back.
But
to
also that is
Tully-Fisher.
observations, right? The shaded regions.
The yes and no. So Reed et al. This is right. So it's an abundance matching. They're all abundance matching techniques, right? So Reed actually did isolated dwarfs and
So when you say abundance matching, you mean in order to infer the mass, I don't see how you get a scale from that.
okay. So I mean, all they're doing
I
is
mean, the
taking a
sequencing.
yeah,
but
they're
not
taking a dark
an
matter
absolute
simulation
scale.
and a luminosity function, right? Dark matter mass function, halo mass function, and luminosity function, assuming a
But you
one-to-one
have a real
correspondence.
scale on it, so.
Well, I'm not quite sure. Like, so if you kept going, there really would be, you would see Milky Way mass scale, like there's an inflection point. But I'm not sure exactly.
We can talk about
Okay.
it. I thought you said you're using abundance matching to determine the mass.
They are. I'm comparing.
So the shaded are doing that and yours
Yes.
are just.
Yeah. And the blue and the pinkish here are actually using satellites of the Milky Way and abundance matching to a dark matter only simulation, right? So that's how they're doing that. So with all the caveats. Okay, so maybe the main takeaway here is that this region right here, right, you can see there's this tighter trend in the abundance matching up here. That is has been well fit by many studies, right, over and over again. And so traditional abundance matching goes down to about, maybe about 10 to the 10 at best. And they do find that there is a tight relationship between stellar mass and halo mass at those scales. This is actually a prediction, right? Nobody's ever been able to do this except with Milky Way satellites. So the whole idea here was to predict what is the stellar mass to halo mass relationship at these low masses. And you can see what we've done is fit a slope and we fit a scatter, and you'd actually fit two, right? We fit a break in this relationship, and before you might be looking at this and going, really, you fit two lines?
Oh, sure.
You see it? So I include this. This is Sandra at 2 different resolutions because it's a little more obvious here that there really does seem to be a break, right?
What are the purple points here?
That's everything combined, and this is just Sandra at 2 different resolutions.
Everything meaning all your simulations.
All Marvel, all Justice League, everything, yeah. But this is because of reionization. Let me just jump to the point, right? So reionization is setting some scale below which it starts to suppress star formation. It doesn't stop it entirely, right? But it creates this bend downward.
Really?
Yeah.
But
Now-
that's happening when these things are really tiny, though.
Sure. Yeah. And also keep in mind, right, the simulation volumes assume that reionization happens everywhere at the same time, right? It's
Right.
not patchy like the real universe probably is. So with those caveats, we get a break. And that might wash out that break in the real universe. Okay. Main takeaway though, as you go below this halo mass, or about 10 to the 10, you also start seeing that the scatter blows up. Okay. And so the reason we wanted to do this is because this is going to, if the scatter blows up at the low mass end, it can impact the number of low mass galaxies that we will see when LSST comes online. And that's because, thanks to CDM, there's more small things that can scatter upward than big things that can scatter downward. And so it changes the slope of the stellar mass function. Right? And that's what this is showing. So here we have, if you had no scatter, if you had constant scatter, and then in red is actually the scatter that we find. And actually it turns out, even though you see that big blow up in scatter at the low masses, it's not having a huge impact on how many small things that we would predict LSST is going to find. So maybe that's reassuring, right? That assuming we understand something about dwarf galaxy formation, this is what we might expect to find without huge amounts of uncertainty. A little processing here. Okay. All right, so let me talk a little bit about how this fits in with other simulations. Okay, so I'm going to blow this up. This is the stellar mass to halo mass relationship again. But now I combed the literature for a day and put every other Zoom simulation I could find on here to see how we all compare to each other. So the Marvel and Justice League are the black points, right? And so you can see they're sort of the largest sample on the spot. In general, I'd say we're actually all in pretty good agreement, right? There are some known outliers, like Auriga. It's sort of known that Auriga tends to make fairly massive galaxies, is I think how they usually put that. And then the other outliers are these Ravaz and Jablonka dwarf galaxies. These were isolated dwarfs that they ran, and the dwarfs used up all of their gas and just became dwarf toroidals in the field, so they probably consumed a little too much gas there. But otherwise, I would say we're all in decent agreement, and that is actually not what other simulators have concluded, right? Actually, other simulators have said that we disagree strongly down in the range of the ultrafaints, and I think that was just because people would run 4 dwarf galaxies or a few dwarf galaxies, but they didn't see the full range of the scatter, and once you see the full range, then it's not clear to me that we disagree very much at all.
Did any of these include dwarf AGNs? Or is that
All of mine do.
all of yours?
Yeah, I don't.
Because is that known now observationally that they pretty much all have that, or?
No, it's not. That's a whole separate talk though. But I can
Yeah.
show you. Yeah, we have occupation fractions of about 1, about 10 to the 9, I think, in halo. Maybe no, in stellar mass, and then it starts to tank below that. But
Right, which observationally is being tested, right?
it's consistent with that. Yeah. That way.
So just so I understand, you're saying that if you take 5 galaxies from one, 5 galaxies from another, it's easy for them to be a factor of 10 different.
Yeah.
Because the intrinsic scatter is like a factor of
It's
100.
big. Yeah.
Yeah. Okay.
That's at least what we would say. Okay, so that's stars. Now I'm going to actually look at stars plus gas. Okay, and that's where I think we start to differ a bit. Okay, so now I've got mass of the galaxy, and by mass of the galaxy I mean stars plus H1 gas. And now I've normalized it to the cosmic baryon fraction as well. Okay, so I highlight this region here a little bit in cyan just because this is where I think we start to disagree a bit. If you look now at fire versus the Marvel runs, right, you start to see a little bit of separation in the two. And so because we agreed well in stellar mass, I think what that means is we have more H1 than fire does. And then
In fire, these are isolated things in fire?
Yeah.
Okay.
Yeah. And then the final plot I've got here is that gets cut off is the it's everything. Sorry, so it's stars plus H1 plus the CGM, so it's all gas in the galaxy as a function of halo mass. But the thing that I find interesting here is now we kind of start to agree again, which says to me, you know, if fire is less H1, they must have more CGM than we do in order to bring the two sets of simulations into line again.
And Apostle didn't distinguish between these different types of gas or something?
Which one? Apostle is on here. Let me see. Let me go to the summary slide here.
It's not in the middle one.
Right. Yes. No. This was. I couldn't find.
Yeah, they didn't publish
this
a
set
number,
of data. Right. I could find all, but I couldn't find H1.
Right.
Yeah.
So you mean that the red moved up towards the black? Is that the main
Yeah.
difference?
Yeah, I think so.
Because as far as I remember, like the Fire 2 don't really do AGN very, like that's what they're planning on doing in Fire
Yeah.
3, right?
But there's no. I mean, there's not a whole lot of evidence that AGN alter the evolution of galaxies at this point.
Okay.
We found some active black holes, but there's nothing that says that they.
So feedback is
Yeah.
more driven by the star formation.
As far as we know.
So should we be surprised at all that there's so many values that are below 1 on the x-axis, on the y-axis? Like, is this related somehow to the missing baryons problem or something like that?
You know, so most of these down here are going to be ultrafaints, right? These are all ultrafaints basically, and so they are suppressed by reionization, and then they've lost all their gas. So that's the prediction, right? I don't think that's inconsistent with ultrafaints, is it?
I'm asking, even like at the high mass region, a lot of those
Oh, here.
a lot of those
like some
are
of these, maybe.
below 1, and you're normalizing to.
I'm normalizing to the cosmic baryon fraction, so technically we should all be closer to.
You should also scatter around 1,
Wait,
shouldn't
oh no, M halo, you're right. Yeah, we should all be about 1. Yeah, so right, no, this is, so yeah, they've lost 90% of their gas, right?
So then a lot of the baryons are just in the interstellar,
Yeah. Intergalactic.
Galactic.
Or it could be hot gas, right?
No, in this plot,
Oh, in
that
this plot is
includes hot
everything,
gas,
you're right.
yeah,
Yeah.
so, yeah. Yep, so you can see some real separation there too, right? So we definitely have different predictions about what's in the CGM. in
How
these
did you
galaxies.
adjust your feedback and so on?
I mean, they're the same in all of the runs. This was, you know, many years ago now. We would have run these to make sure they match, say, the stellar mass to halo mass relationship where abundance matching had been done, and that was pretty much it. And then the rest of it's all prediction. So rather than putting it on this confusing plot, I'm actually just going to show this is the H1 mass in these simulated galaxies now as a function of B-band magnitude, because that's what was available for figs. This is an actual survey, right? But all they had available was B-band magnitude. And so point being that it looks like, you know, the H1 content of these simulated dwarfs matches the observed dwarf galaxies pretty well. Same thing here with morphologies. Okay, so, right, I mentioned that some of these LMC-mass things that I was running were disky. Here, this is the edge-on axis ratio, so B to A. So we have, you know, if you were looking at the thing edge-on, it's the short to long axis ratio. And the black lines are real observed dwarf galaxies from Sanchez, Janssen et al. This is the mean of their dwarf galaxy sample in the solid black, and then the dashed lines are the 1 and 99% regions. And here's, you know, all of our dwarf galaxies in here. So they span the range pretty well in terms of matching the observed morphologies.
But you've chosen some particular. This is projected or not projected? I mean, the observations are projected.
Right. We are doing it both ways. So this plot is being updated with projected, but yeah, this was just measured directly from stellar. Well, either there's a mix of some images where we fit the axis ratio, and there's a fit where we just fit the morphology of the stars.
Right, but the red dots are some intrinsic V over A or something.
Yeah.
Okay.
Right. But we're remaking this plot compared to the Kato-Fong shapes.
Right. Yeah. Okay.
Yeah. So hopefully next time I get this, we'll have one of that. But I wanted to point out that this is different, right, than fire, right, where the dwarf galaxies are all very thick. They have axis ratios of 0.5 and higher, right? So we're definitely seeing some differences in our dwarf galaxies, and I think, you know, it probably has to come down to this, right, this complicated plot, which I'm going to walk you through. This is a great plot from Karthik Iyer's work, where he looked at the power spectral density in these various simulations, right? So I always have to put this up here to remind myself what it is. At any time scale, it's a measure of the amount of power contained in the star formation rate fluctuations. So in other words, it tells us about the variability or the burstiness of the star formation on a given time scale. Okay, so here are the actual star formation histories for a bunch of runs from both Fire and the Marvel and Justice League stuff. And right, so up here are the Milky Ways, and we each contributed a dwarf, if I remember correctly. And in fact, this gray region right here, that's what's shown in this plot. And so I actually wanted to point out that, see, the purple here that's one of the Fire galaxies, M12M. No, wait, I'm sorry, that's Sandra. And then the gold is M12F. Right, so we actually have like these star formation histories that are nearly identical, and yet if you look at the burstiness, the Fire Milky Way is burstier than Sandra. Sandra is actually not the dashed line; it's this one. So this is the difference that we're talking about. And the dwarfs are all. Here's the dwarfs. The M11Q and Rogue are all pretty bursty, right? They're burstier in general than Milky Ways, but the Fire dwarfs and M11Q is always burstier as well. So Fire is just burstier than our runs, and so I think that's probably what is setting some of these differences in morphology, CGM, etc. Ask me to understand exactly why this is happening, and I can't necessarily tell you, right? But they are definitely burstier.
Why would that cause them to be thicker?
You know what, I'll come back to
Okay.
that. Will I get to it? I may not get to it until towards the end, though. So let me. One of the major differences I think that is going on is that Kareem El-Badri showed that some of the stars when they're being born in Fire are in these cold gas clouds that are being pushed out, or even the ones that are like cooling back to the center. So they have. I'll just jump to it. Can I jump to it right now?
Probably.
No. No.
Oh, because you have to.
No, yeah. So anyway, so the stars have these high radial velocities when they're born. Okay. And we do not. Okay. And in fact, that's a little bit apparent.
Weird.
It's a
It's true.
The third one was it's accelerating.
Approaching.
It's like, oh my God. No, that's not right. I'm gonna stop the share.
yeah, that's good.
There we go. But am I stopping the share?
You are, because this is showing your screen.
All right.
What's
So now, what do I need to do? I need to
Wait,
share
before-
again.
First go to Zoom. Okay,
Okay,
and now
and sharing here.
I think so.
Mm. Yeah. Okay. No.
Alright.
Hopefully that will stop. Okay. So one other way this manifests is in the velocity dispersion of stars in the two different simulations, right? So what you are seeing here is the z velocity dispersion in and out of the disk of the galaxy as a function of age. In one of, this is actually an older simulation, H277, and this is actual data from the Geneva-Copenhagen survey, I believe, in orange. Okay, so this is the age-velocity relationship for stars in the solar neighborhood. And you can see the simulation actually does a pretty good job. The black line is directly from the simulation, and then the gray bands are when you account for age errors in the observations. Then they match very well.
I want to be sure I understand properly what you mean by the sigma z.
Yeah.
It's just literally the vertical motion.
Yep. Right. This is coming from two things. Okay, so the black line here shows you the sigma, the z velocity dispersion of the gas, the cold gas that's forming stars as a function of time. And so you can see that's decreasing with time. But then these colors are different mono-age populations that are being born from this cold gas. They have the same velocity dispersion at birth, but then you can see they get heated up. Each of these gets heated up a bit. And that's actually perfectly consistent with a model in which they're scattering off of giant molecular clouds and being heated with time. And so this result in the solar neighborhood is a combination both of the declining velocity dispersion of the parent gas particles, but also this heating as a function of age. So that is different in fire as well. Okay, so here is, all right, now I apologize. So here I had sigma z, now I've got total velocity dispersion. Right, but here is the Milky Way and M31 data, and these are the fire galaxy Milky Ways. Right, so they have very hot disks, and so I
That's
think
extremely hot disk.
and
oh
so I
my
think
Lord.
it's a lot of this quirkiness, right? I think that's what's going on.
How do they even form disks? Like, how do they have an old stellar disk with a sigma of 200?
Actually, that's not clear. There's a real debate right now because they form thin disks late, and it's not clear if they have old thin disks. This is also, I just want to show it for a dwarf galaxy, same thing. Here's a simulated dwarf galaxy, right? Our velocity dispersions, this is again, total sigma. The stars are being born with just a few kilometers per second dispersion. This is where those stars end up at redshift 0, and then the black data points compared to WLM, just showing you that they're a pretty good match to observe velocity dispersions in local volume dwarfs. And again, that's also consistent with just a model where we sent, well, here's a merger, but this is consistent with just them being scattered off of giant molecular clouds and heated with time. All right, so now I'll show some other results, and I figured that I'd start by showing another pretty movie. This is like my favorite movie of Sandra. Sarah, this should be right up your alley. So this is the formation of the stellar halo in Sandra. So you're only seeing stars in this movie, and they are color-coded entirely by metallicity, and so you can see these just beautiful stellar streams being formed in the halo of this galaxy. The main Milky Way is saturated. It's down here at the center, buried in the white. But in the meantime, you see all this lovely structure in the halo. And then as time goes on, the reason I really like this is that there is a galaxy that's going to infall pretty soon, LMC-ish in mass. There it is. It came from the background. Oh wait, no, isn't it? Yeah. I'm not sure. Yeah. Okay. So it's going to get shredded, and you can see it's more metal rich, and so it's actually going to turn most of this halo like red because it's like the dominant thing in the halo, right? Anyway, and now I'm not going to talk about stellar halos at all. I just had to show this really. So. All right, so I'm going to talk about again dwarf galaxies. All right, here is what you're seeing in blue is Sandra and Elena at our high resolutions, which we call our mint resolution. Right, sticking with the comic book theme, they're like our mint condition, mint resolution runs. And so this is the size, luminosity of those compared to. So now you can see that thing up there. That's really nice. Compared to local group data. Huh?
Sorry, go on.
Okay. And just so you know, there are some inherent problems with or limits to the simulations, right? So here's basically you shouldn't trust anything smaller than this, and here's where 50 stars get cut off. So these all have more than 50 stars in them, but you can see they match pretty well to the local volume data in that range. And part of the reason they match, part of the diversity in the sizes and in this, right, so now we have stellar velocity dispersion. And again, there's a huge range of values especially at the lower luminosities. And that's being imprinted on it because of the environment, right? So because they are evolving in a Milky Way mass galaxy. So for instance, these things down here, these 2 km/s dwarfs that we end up with, they get there through tidal stripping. And that's what this plot shows. This is the stellar velocity dispersion as a function of the halo mass of the galaxy currently compared to its peak value. Right, so they're color-coded by their peak halo mass, and essentially as things get stripped, they move this way in the plot. And so to end up down here at 2 km/s or so, you've lost 99% of your stellar mass. Or sorry, not your stellar mass. Kept your stellar mass. You've lost your dark matter mass. And in fact, this star here, that's actually a backsplash galaxy. So this thing is sitting outside of the Bureau radius of the Milky Way, but it's been substantially stripped before it got back up there. Right, so that's what's sort of imprinting this huge range of velocity dispersion.
By backslash galaxy, you mean a galaxy that's gone. It's formed as a galaxy, but then gone through the Milky Way.
It's gone through the Milky Way.
That's not a tidally formed galaxy.
Correct.
Okay.
Yeah. All right, so here we come back to some predictions for these surveys that I mentioned earlier. Okay, so lots of information on these plots. Let me walk you through it. This is T90 or Tau 90. You'll see this multiple times, and this is the time at which the galaxy formed 90% of its stars. Okay, and then down here we have the time where it fell into twice the virial radius of the Milky Way halo. Right, and we used this as infall time because things start getting stripped even before they hit the virial radius. So, for example, there's this population of sort of massive galaxies up here that basically stopped forming stars soon after they fell into the Milky Way. But I actually want to focus on these things. These are all things that stopped forming their stars about 2 to 3 billion years after the Big Bang, and that's because of reionization. Right? They're all low mass halos. They were all shut off by reionization. But the lower plot shows you H1 masses at infall. And this is what I find interesting, right? Here you have a whole bunch of things that are no longer forming stars, but they have gas masses of, up to 10 to the 5 in H1 as they infall into the Milky Way. And the right-hand plot shows the H1 to stellar mass at redshift 0 as a function of distance from Milky Way. And long story short, the things in red are basically ultra-faint dwarf galaxies that have enough H1 that something like Wallaby will be able to detect them. Okay, so that's the first prediction there. I think we're going to find a whole bunch of gas-rich ultra-faints in the field. Let's see. That aren't even forming stars, right? They're actually shut off, but they've got H1. We'll see. Okay, next prediction. All right. So here again is the stellar mass to halo mass relationship. And now what I'm doing is the circles that you see are all isolated central field dwarf galaxies. And the black, or sorry, not the black, the squares and the stars are backsplash and satellites. And so as we flip between those two different populations, you can see that there's a shift, right? Especially when I look up here compared to the read, you really see sort of a jump between the two different populations. And that is what this plot is trying to bring out. This is the stellar mass at redshift 0 compared to the peak halo mass as a function of peak halo mass. But now these points are color-coded by how far they are from a massive galaxy. So massive is 3 times 10 to the 11 in halo mass, so sort of like an LMC shape. And what hopefully you see is that there's a gradient from purplish down to yellow, right, as you go this way in the plot. And so essentially things that are further away from a massive galaxy are sitting at, they have, I mean, they have lower stellar masses, really what it comes down to.
Do they have lower stellar masses, or you have higher, what is the thing that happened?
So
they didn't form as many stars, or something happened with the dark matter?
Both the star formation and the halo masses we've been able to determine are delayed compared to the stuff that's nearby.
Wait, is that because they get stripped maybe of H1 as they fall nearby, and that could be causing it? Because I don't see what would make them have less stars further away.
They do though. When you account for the H1, just because you brought that up. So this is I find this really interesting, right? When you put the H1 back in, that difference goes away. Right? So the total baryonic content is the same. It's really less stars. And the other thing I found fascinating about this plot
is
is
less stars for the centrals.
Yeah.
Oh.
That's what you're saying?
And the centrals mean near a big galaxy.
No, the centrals mean isolated.
Isolated, yeah.
Oh, but these are centrals that don't have these are isolated centrals.
These are like 3.
There's nothing bigger than them near them.
Right.
That's what's meant.
That's what I mean.
And then they have less. Or was it maybe tidally induced star formation that made the other ones have more?
I don't know. I mean, so my theorist brain thought this, right? Okay, I see galaxies as giant Gaussian overdensities, right? So Milky Way is a big Gaussian overdensity, right?
Gaussian.
Okay, well, right? So it's an overdensity. And then a satellite is another little overdensity sitting on top of that. So it gets like a boost from the Milky Way in my brain, right? That's what happens. It gets like a little density boost, and so maybe that increases the star formation rate at early times. And then things that are far away, they don't get that
more
boost.
stuff to accrete, you're saying. Yeah.
They don't have that boost,
Early
and
on.
so the star formation is delayed.
But it also has more dark matter it can accrete. Like
It's
somehow
not it's delayed. I mean, it's really the formation
It's
times
the
are delayed.
time.
Yeah.
But there's no chance that in the satellites you're stripping dark matter preferentially?
Yeah, this is peak though.
That's peak. Sorry.
Do the isolated ones in the satellites that are more in the overdense region, do they have similar masses?
Yeah.
Okay.
Yep. So there you go. That's a prediction. There's two things I find interesting about this. So in some sense, when you think about just the centrals, the isolated ones, this isn't surprising. The fact that the relationship gets tighter, because the baryonic Tully-Fisher relationship has been telling us for years that when you add in H1, you have a tighter relationship with halo mass. So maybe that's not surprising. What is surprising is that nobody's ever thought about the satellites when they're talking about the baryonic Tully-Fisher relation. And there's no reason a priori that I can think of why they should fall in the same relationship, right? So. This has other observational consequences which are much easier to test, right? So again, here's T90, right? The time when you form 90% of your stars. So as you are out here closer to 14, this is time since Big Bang. So 14 is present day, essentially. And so these are all, massive galaxies that are still star forming further away from the Milky Way. That's great. That's consistent with what we see observationally. Nearby, here's a bunch of quenched satellites, Good, okay, that's great. We already knew about that dichotomy. But now you can see that we really, we have this extended star formation even down, here's some ultrafaints that are still star forming, right? or at least were star forming recently. And so that's sort of the next prediction, is that we're going to see all these late forming, galaxies as we go
Wait,
through.
sorry, it's taking me a while to
Yeah,
process this.
There's a lot of stuff.
The
Yeah.
upper right is isolated things that are 10 to the 8
Yep.
and old.
No, not old. You're young. So this is time
Which
since
direction?
Big Bang. Yeah, and that will flip on you in the next plot. Just to apologize
Awesome.
in advance. Yeah. So this is time since Big Bang. So
Okay.
this is today. This is Big Bang.
Oh, and so you're pointing out that when you're pointing out the star forming ones, those are those
you're
cyan
pointing at the
ones.
blue, I
Yeah,
I mixed
sorry.
it up too.
Yeah.
No.
Okay.
Yeah.
All right.
Okay.
Wait.
Yeah.
Okay. Great.
But the upper right is good.
Yeah.
Upper right works.
Okay. Yeah, so this is, now I've flipped it. Now, actually, my grad student, Claire Riggs, has flipped it. So now we're looking at look back time rather than time since Big Bang. I'm sorry. So smaller numbers is more recent star formation now. But she took all these simulated galaxies, binned them as a function of distance to a massive galaxy, and then what she's plotted here is the mean T90 in each distance bin. And you can see there's a clear trend, right, that comes out of this. Right. You want me to keep going? I can probably at least get
You're
through
about 5
gradients.
minutes.
Oh,
so-
okay, that should be, I think this is my last topic, so.
Okay.
Oh wait, so sorry to do this, but the
Oh,
previous
go
plot kind of makes sense for it being tidal though, right? So if they're further away, it's easier for them to still have star formation happening because their gas hasn't been stripped tidally. Could you see it that way, or that's not right?
That is certainly, I'm sure, part of it.
Because I think it was
I
opposite in
think-
my brain before, which hurt, but now I don't know.
Yeah, no,
Yeah,
I mean,
if
there's,
lower
there's-
is younger,
there's-
this makes sense.
yes.
Yeah.
However, I think this was selected to not account for any of that. This is like, gas-rich field works kind of thing here, so.
I see.
And so it's there, even if you cut out the satellites, the trend is still there. Yeah. Blown to mind.
Right. Well, you have to be careful about other things that are around, right? And then because when you do this observationally, you always have to be there. You get these effects that are way outside or megaparsecs, but you need to.
Okay.
But a lot of that comes from like secondary effects because overall the density is lower, and so there are other things around.
Sure.
Right? Anyway, go on.
Okay. All right. So the last thing I want to talk about was age gradients in dwarf galaxies. Okay. So I don't, people may be familiar with the fact that the Milky Way essentially we think has grown inside out, right? So the older stars are in the center, and then as the disk has grown with time, as it creates higher and higher momentum material, and so the younger stars are on the outskirts. Dwarf galaxies look totally the opposite. Okay, so they actually have young stars sitting in the center, and all their old stars are sitting outside. Okay, so they look like they formed from the outside in rather than the inside out. And this is true whether you're talking satellite dwarf galaxies, dwarf spirals, dwarf regulars, dwarf transitions, it doesn't matter. Whatever dwarf you're looking at, it's got younger stars sitting in the center. And you can kind of see that here. This is an image of the Phoenix dwarf galaxy, and you can kind of see that it's got lots of blue young stars sitting in the center, and then most of the stars in the outskirts are redder. And if you can't see that, I'm just going to guide your eye. It looks like that. Here is a simulated dwarf. It's about the mass of WLM, stellar mass of about 10 to the 7. So my grad student Claire Riggs has binned all the stars in this galaxy according to their formation time. Okay, so now we've got, all right, this is look back, or the age. It's age. Let's just say it's age. So older stars are about 14 billion years old, right? Most recent stars are less than a billion years old. And so what you're seeing as you go this way, right? This is the average formation radius. So the old stars are forming closer to the center, younger stars are forming further out. Okay, so that's an inside-out formation. But if you look at where they are today, they're sitting further. The older stars are sitting further out. So they look like they formed outside in. Okay, so the stars got reshuffled. That's pretty much what's going on here. And we think that's probably due to the same process that's creating dark matter cores in these simulations, right? So many of you are probably familiar with this fact that if you have this bursty star formation history, as you kick the gas out through supernova heated feedback after a burst of star formation, that fluctuates the gravitational potential well at the center of the dwarf. And so, the potential well expands, orbits expand of the dark matter, and then later the gas can cool back to the center, and it brings the orbits a little bit closer back in, but you keep undergoing this bursty star formation over and over again, and you keep kicking dark matter out of the center of the galaxy and create, this is what happens. You start off with a steep cuspy profile, density profile of dark matter, and with time you transform it into a core as you undergo this burstiness. Well, dark matter particles in these simulations are collisionless, so are stars. So the same thing that's happening to the dark matter should be happening to the stars. And so, I probably should have rearranged this plot. So we think that's what's happening, and I just wanted to show the full picture here. So now we've got T90, time since Big Bang. And we're measuring age gradients as the difference in T90 if you measure at the center of the galaxy compared to the effective radius. And so that's what this is, dT90 over the effective radius. So we have, things that are more recently star forming have actually fairly flat gradients, flat age gradients. And these oldest things also have very flat age gradients. But then there's sort of this U shape in between, right? And you'll notice that satellites and field dwarfs are basically doing the same thing. So this plot brings in the dark matter core slope. So things that are cored are up here between about 0 and -0.5, and things that are cuspy are down here closer to about -1.5. And so if you just look at this sort of diagonal part of the plot here, right? These are old low mass galaxies. Right? They probably don't have enough star formation to be bursty. They have like a burst and then they die off, or they're impacted by reionization or something. And so they stay cored. But then as you head up this way, you get to these more massive galaxies that are able to make cores and continue star formation for longer. And so we think that's what's going on as you head basically in this direction. Now, you may notice there's also this whole line, though, of cored galaxies that have a range of age gradients. Okay? And they're all cored. And that's what this plot tries to dissect. Now these are color-coded by T90, and so you should see a color gradient. Basically, as you head this way, these things have flat age gradients. They also have more recent star formation. And so what we think is happening is that the dwarf galaxies that have had more recent star formation, essentially they light up everywhere at once, and they erase the age gradient. And so that's the second part. This is a really tough one to digest. I probably lost, 99% of you. So let me take it down to something simpler, okay? We are not the only people who have looked at age gradients. Right? The Fire Andrew Grouse and the Fire team looked at age gradients as well. And this is their version of this plot. Again, T90 between 0 and 1 effective radius, and look back time now. Here are the Fire dwarfs. Here are our dwarfs. We look like we're in excellent agreement, right? Okay. However, if you measure T50, we are not in excellent agreement. Okay, so this is the same plot from Fire, but now instead of measuring T90, the time when 90% of the stars form, they've measured T50, the time when 50% of the stars form, and they essentially find the same thing as when they look at T90. There's no difference between T50 and T90. If we look at T50, we get a scatter plot. And so one of these is look back time, and one of these is time since Big Bang. So I'm just going to flip this plot on you so you can compare. But one, it's a scatter plot, so it doesn't really matter, right? Like, we don't find a trend. And so what that says to me is that the processes that input the gradients in Fire are happening before 50% of the stars are forming, whereas in ours it's happening at later times. And so this comes back to, this is that plot I was mentioning earlier, where this is from Karim El-Badri's work on the Fire dwarfs. Right? So here is the star formation, specific star formation rate actually of this dwarf galaxy. You can see, as it really is quite bursty. Here is the star forming gas, the radial velocity of the star forming gas, and you can see it's just matches very nicely onto the specific star formation rate. So the gas is being pushed around by this bursty star formation. And then here are the young stars in blue that are forming from this gas, right? And so the stars are born with this young radial velocity at young times. And so I think that, you know, if this is what's setting this gradient, then that's, I think, the difference. And so my main point, this is my last point, is that if we can measure this in dwarf galaxies, and we can using resolved star formation histories, if we can do that, then we have an immediate discriminant, right, between the two different feedback models. So that's where I'll leave it. So the whole point being, we've undertaken this huge campaign to try to make these observational predictions, and I basically just highlighted the first few predictions today that also really, test feedback models in these different simulations. So the gas content, the star formation histories, velocity dispersions, and age gradients in dwarf galaxies. So, thank you.
Got more questions?
Are you gonna be around?
Yeah, for a couple
I
hours.
have to do a Zoom doc.
I have one question. So about the part where, this might be a naive question, there's a part where you showed the sort of the inside out behavior of the stars being produced. What I was wondering is there a way that you can tell whether the stars in the inner part are later generations of the stars being produced?
I mean, these are color coded, right, by the time they were formed in the simulation.
Right. So the ones in the so I guess for example in this simulation, how old is this cluster?
Oh, sorry, this is a real dwarf, but yeah. So I'm not quite sure.
Okay. Well, in the simulations, so these have ages of about 8 years. So I guess it's enough for maybe a couple of generations start forming.
I mean, it's been forming for 14 billion years.
Okay, so these are all the first, these stars are the first stars that are being formed in those regions.
For these, you mean?
Okay.
Yeah, these are the oldest, so these are the first stars that formed, and this so yeah.
So they couldn't have been replaced, in other words.
Oh right, yeah, exactly. Yeah.
Okay. All right.
Yeah. Right. Yeah, mergers don't seem to have any impact on this, right? It's not like we're bringing in old stars or things like that.
Okay.
Yeah.
And in this the smaller scale, like these are not small enough that two-body interactions, like star-star interactions, you have to worry about that or not?
Stellar particle interactions, you mean, or?
Well, I mean in the real universe, are smaller scale scattering processes important? Like in a stellar cluster, you would expect like mass segregation.
You would expect that on these scales.
You don't expect that
for? Not that I'm aware of.
Okay.
But just to be clear, we've cut out all the
I guess
the
you have
small
10 to the
things
7
where we worry
stars,
about numerical effects like that too as well.
Yeah. Yeah, I guess if you don't have the numerical effect, okay. Other questions? I want to thank Alyson again. Yeah, we're gonna miss you next week. Actually, based on this.
Oh.
In Tucson.
Oh.
Yeah. Jorge Moreno and I are supposed to lead a discussion about feedback.
Oh my gosh, yeah.
Yeah.
Right. I love feedback.
But a lot of this later stuff is these specific things aren't published yet.
Like Charlotte had a baby a week ago, but other like we're literally adding this plot into this paper and then it's been done, kind of thing.
Right, I'm familiar with that phase of paper writing.
Yeah, that's where we're at. Yeah, so like where do I have any of this? The age velocity stuff is published.
But was that a Milky Way?
I had dwarfs and Milky Way.
You had dwarf and Milky Way.
Yeah, so here's both, right?
Here's... I should be turning off the recording probably.
Thanks, Alyson. Really
Well, I
appreciate it.
left the Zoom though, so that.
Yeah, but it'll still be recording us from here.